Hi, David Hilderman here. We know a few things with reasonable certainty regarding carbon dioxide on Earth. World annual carbon dioxide emissions, measured atmospheric carbon dioxide levels as taken from a mountain in Hawaii and shown by the red line, the trend expected from fossil fuel burning, which is the atmospheric carbon dioxide levels that we would have had if the Earth's sink rates stayed the same and didn't increase with man-made CO2 emissions. Here are some simplified terms that I will use going forward. Plants will be used as a term for all photosynthetic organisms. They use or absorb carbon dioxide and are the carbon or CO2 sinks on Earth. Animals will be used for all aerobic organisms. They create carbon dioxide and create the natural carbon dioxide emissions on Earth. Anything that adds carbon dioxide to the Earth is called a source. This includes animals and man-made activities. Anything that removes carbon dioxide from the atmosphere is called a sink. In most cases, plants. Here is a simple model to describe the Earth's atmospheric carbon dioxide. The water depth is like the atmospheric level of carbon dioxide. Water entering this upper pipe is like carbon dioxide entering the atmosphere. It's the carbon dioxide source. Water leaving this pipe is like carbon dioxide leaving the atmosphere due to it being used by plants. It's the carbon dioxide sink. Here is a simulation of the Earth's atmosphere with the addition of fossil fuel burning and ignoring natural carbon dioxide sources and sinks. We plug this bottom hole and we add water through this pipe. Water will then rise in the tank. So, if we ignore natural cause carbon dioxide sources and sinks and only looked at carbon dioxide emissions from fossil fuels, this would give us the trend expected from the fossil fuel burning, as shown in the graph from the World Meteorological Organization. This shows annual carbon dioxide emissions in megatons per year from 1960 until 2020. This is the same period as the measurements from Hawaii. If we accumulate the emissions, we get this graph. They accumulate to 1.3 trillion tons of carbon dioxide from 1960 to 2020. Here's the graph from the World Meteorological Organization and my graph of accumulated human emissions. By using a ratio of deltas over the period of 1960 to 2000 between the trend expected from fossil fuel burning and the accumulated emissions, we calculate that an increase of 7,862 megatons of carbon dioxide in the atmosphere increases the atmospheric levels by 1 part per million. When taking numbers of the graph from the World Meteorological Organization and comparing it to values calculated from the accumulated emissions, I found that the deviation to be less than 0.5%. Scientists estimate that there are 750 gigatons of natural carbon dioxide emissions per year. These are created by animals. Before burning fossil fuels, carbon dioxide emissions and sinks were equal, and as a result, the atmospheric carbon dioxide levels remained constant at about 280 parts per million. Let's look at the model again in this light. So, 750 gigatons of natural carbon dioxide emissions enter the atmosphere every year. At the same time, 750 gigatons of carbon dioxide were absorbed by plants every year. Atmospheric carbon dioxide levels remained at a constant level of 280 parts per million. Let's add human emissions to the model. Let's keep the water flow constant at 750 gigatons per year in the first upper pipe to model naturally created carbon dioxide emissions. Let's add a second upper pipe to represent human-caused emissions. Since we have been burning fossil fuels, it is like a hose has been attached to that second pipe, and we have been continually turning the hose up. The carbon dioxide levels are rising, and as a result, the carbon dioxide leaving the atmosphere is doing so at increasing rates due to increased plant growth. So this is data that we have for the model. We have measured carbon dioxide levels in parts per million from 1960 to 2020. We have the amount of carbon dioxide required to increase atmospheric carbon dioxide by 1 part per million, and that's 7,862 megatons. So that's the amount. If you could just add 7,862 megatons of carbon dioxide, just boom to the atmosphere, the level you would measure it would actually go up by 1 part per million. And we also know man-made carbon dioxide emissions from 1960 to 2020, and the amount of natural emissions per year, 750 gigatons. Now, this is all data that I found on the internet that talk about carbon dioxide in our atmosphere. So here's how the model works. Total annual carbon dioxide emissions are accumulated starting with an initial amount. This is the first value to be adjusted and simulates the starting water level in the tank. Let's call that variable A. When accumulating, the previous year's accumulated value is multiplied by a number that is less than 1 before adding to the emissions from the current year. This makes emission sink rates a function of the atmospheric carbon dioxide levels. Just like the rate of flow out of the lower pipe is a function of water level. Let's call that variable B. An example of how the equation is set up in a spreadsheet is shown. This accumulated value is divided by 7,862, which is the emissions to atmospheric parts per million conversion. The resulting values are shifted by the appropriate amount to allow the initial value to equal the measured carbon dioxide in 1960. I then plot the resulting values along with actual atmospheric carbon dioxide levels in parts per million and adjust A and B variables to get the best fit. Here's that graph again from the World Meteorological Organization along with my calculated and modeled results. As I said before, the trend line and the calculated carbon dioxide levels without land and ocean sink plots are identical within 0.5%. The model CO2 levels are plotted over the actual measured levels. Both A and B variables were adjusted until the best possible fit was found. The final results came out much better than I could have expected. By adjusting variables A and B, I was able to match the modeled atmospheric carbon dioxide levels extremely accurately, within 1.5% accuracy. This is a plot of world carbon dioxide sinks versus atmospheric carbon dioxide levels as taken from the model results. Plant growth, as represented by world carbon sinks, is linearly proportional to atmospheric carbon dioxide levels. I would expect this linear range to hold true from about 250 to 800 parts per million. It is interesting that I was able to match actual with models so well with this. The reason I'm surprised about that is because not only does plant growth rate increase with increased carbon dioxide levels, but also leaf cover increases. And this leaf cover takes time to accumulate. On the Earth, plants went from converting 750 gigatons to 768 gigatons of carbon dioxide per year into plant biomass. This is an increase of 13 gigatons per year. Let's see how the model works with some alternate scenarios. With all human emissions stopped at 1960, the model shows atmospheric levels settling to a constant level of 286 parts per million. This is surprisingly close to the 280 parts per million, which is the pre-industrial level. Let's run the model with no human emissions, but having a volcanic event that adds 400 gigatons per year for 10 years, then back to just natural emissions after that. As you can see, the atmospheric carbon dioxide rises rapidly during the volcanic activity, but then drops back to pre-volcanic levels in only 200 years. I believe that things would happen somewhat like this. However, increased carbon sinks that we see on Earth right now are due to increased plant growth rates and an increase in plants. With an abrupt addition of carbon dioxide like this, it would take a while for leaf cover to increase before carbon dioxide sinks would increase to cause the level to drop. Also, a volcanic event would spew out sulfur dioxide and ash, which would likely kill lots of plants and potentially block the sun, which could reduce photosynthesis for a while before increasing. Fundamentals of carbon dioxide on Earth. Water and carbon dioxide are the raw materials for plant growth. This is what plants are made of. Increasing atmospheric carbon dioxide increases plant growth, just as reducing carbon dioxide would reduce plant growth. Carbon dioxide since before life on Earth. Using the analogy of a water tank representing atmospheric carbon dioxide on Earth, let's look at the Earth before life began. Using the water tank analogy to represent the history of carbon dioxide on Earth, I have made this graphic. It's a 2.9 meter diameter, 100 meter high cylinder beside a 1.7 meter tall person. When full, this represents what scientists estimate is the 70% minimum that carbon dioxide comprised of the atmosphere before life on Earth, and it would have stayed that way had life not come along. The first life form on Earth were plants in the ocean. The best guess is that they first appeared 4.6 billion years ago. They used carbon dioxide to create plant biomass and oxygen. Shortly after plants, aerobic organisms, including bacteria, evolved that used the oxygen and created carbon dioxide. Carbon dioxide and dissolved calcium was converted to calcium carbonate by both plants and animals. Limestone is made from this calcium carbonate. This continued to use up the carbon dioxide that was originally there from the start of the Earth. When plants first evolved to come on land, the plants and shellfish had used up most of that carbon dioxide. Only 1 meter was left in the tank. 0.7% of the atmosphere was now carbon dioxide. Life used carbon dioxide faster than it was being created, so it continued to drop in levels until there was only 40 millimeters left in the tank, or 0.028% of the atmosphere. So it went from 100 meters at the start of life on Earth to 40 millimeters, and it stayed there for millions of years. Instead of having a nearly limitless supply, plants now only had what was being created by animals. This is my understanding of the best estimation of the history of carbon dioxide going back 600 million years. It goes back to the earliest fossil records when life first came out of the oceans onto land. Carbon dioxide would continually go down as it was used by life. Volcanic activity would inject carbon dioxide into the system to bring up carbon dioxide levels, but as you can see, it always comes back down to a minimum around 280 parts per million, or 0.028%, which is the same as it was before we started burning fossil fuels. Let's take a look going into the future using the model, this time taking the nightmare scenario for an environmentalist. This graph shows what I will use as human-caused carbon dioxide emissions to predict future atmospheric carbon dioxide levels. Statistica.com predicts that if we go business as usual, we will be emitting 43,000 megatons of carbon dioxide annually in 2050. I'm going to use numbers that I think would reflect successful industrialization of India and Africa. Carbon dioxide emission rates would increase much faster than Statistica predicts, reaching 48,000 megatons by 2050 and continuing to increase at that rate until a peak of 59,000 megatons per year in 2080, and then keeping that level going forward. This is what it came out with. Even with the extremely high annual emissions, the atmospheric levels don't reach 700 parts per million, and this is going all the way to the year 2200. Increased atmospheric carbon dioxide increases plant growth rates. As the carbon dioxide levels increase in the atmosphere, plant growth rates increase and eventually stabilize the carbon dioxide levels. From data that made the previous slide, I calculated the annual plant growth rates, or carbon dioxide absorption rates caused by human emissions. When we increase carbon dioxide emissions, the atmospheric levels increase. Increased atmospheric levels increases plant growth rates, which increases the rate that plants use the carbon dioxide that we are adding to the atmosphere. Given enough time, plant growth rates will increase to the point where it will match the emission rates. This is all based on my model. Here's some information that I feel supports my theory that plant growth rates will rise to accommodate increased carbon dioxide emissions. In BC, between 2009 and 2012, 20 million hectares of forest was destroyed by the white pine beetle infestation. So, some scientists did some analysis of the forest to figure out how long was it going to take for all the board feet lost in BC forests to come back after all the destruction from the white pine beetle. And the result came back that all the forests would be replenished by the year 2020. And that was very fast, much faster than most people thought it was going to be. And the reason is that they found that forest growth rates are increasing in BC at a rate of 1 to 3% every year. So every year, forests in BC increase their growth rate by 1 to 3%. And that's all because atmospheric carbon dioxide levels are going up. So some say that increased carbon dioxide is plant fertilizer. I don't think that's truly accurate. A fertilizer is a trace element that makes something grow faster. Carbon dioxide is more like a raw material for plant growth. It, along with water, becomes the plant. It isn't even accurate to call it plant food. When we think of food, we think of something that gives us energy to live. When plants take in carbon dioxide, it is used to build more plant matter, not just to live. We only hear from the media how everything is getting worse on Earth. This study was based on satellite data. From 1982 until 2015, the Earth gained 18 million square kilometers of leaf cover. This is equivalent to adding the plants of 2 times continental United States to the Earth. If environmentalists had their way and humans stopped our carbon dioxide emissions, 18 million square kilometers of leaf cover would die. It needs the higher levels of carbon dioxide to survive. Let's have another look at historical carbon dioxide levels. Past large increases in carbon dioxide were likely caused by volcanic activity. So things like this, and like this jump here. Actually, any of these jumps would have been due to volcanic activity, because there's no way that you could have had some sea monster that's, breathing and farting a lot to cause the carbon dioxide levels to go up like that. It would have had to have been volcanic activity. So whenever the carbon dioxide levels increased, plants would increase growth and use that carbon dioxide up. And you can see that by how fast, like look at after this jump here, how fast the carbon dioxide levels went down. And that's because plants would have been using it at that really fast rate. And then they would go down until this equilibrium occurred. And that lower rate there is about 280 parts per million, based on this graph there. So it would go down to that 280 parts per million. It would stay there because it can't go any lower. So plants would have to slow down their growth. I actually think that most likely when it got down to this low level, it probably a good portion of plants died because plants would have been used to much higher carbon dioxide levels. So I have a feeling that when it got down to that low level, a whole bunch of plants became extinct. And then, anytime that it bounced up again because of volcanic levels, you see the carbon dioxide would slowly go down again. So our current levels of carbon dioxide are higher than they have been in 5 million years, and plant growth is also higher than it has been in 5 million years. Burning fossil fuels increases carbon dioxide without the destruction of volcanoes. So I think you could argue that burning fossil fuels, it's been a benefit to humanity, and it's increasing life on the earth. It's increasing plant growth. And I'm sure that there's animals and there's other organisms on earth that are benefiting from this increased plant growth. So this is my conclusion from all this stuff. Some really basic things and some other things that I'm kind of being subjective on. Carbon dioxide and water is what plants are made of. Carbon dioxide levels are higher today than in 5 million years, and plant growth rates are higher now than they have been in 5 million years. Prior to burning fossil fuels, plants were limited in their growth rates by the carbon dioxide created by breathing organisms. If we allow carbon dioxide levels to continue to rise without restrictions, plant growth rates will rise to accommodate the increased levels, and the earth, all animals and plants, will have the benefit of significantly increased plant growth. It is reprehensible that these facts regarding the positive effects of carbon dioxide are being hid from us. The idea that my analysis is new is not possible. There must be other scientists who have done the same analysis and have came to the same conclusions. Why is it that I've never heard this before? Why did I have to figure this out on my own? So that's it. That's my presentation.